Welcome to Astro Odyssey. Explore the universe. There is a quiet, burning star at the center of our solar system that most people rarely think about. It rises each morning, warms the air, lights the sky, and disappears each evening without much thought from the billions of people living under its glow. It feels stable, predictable, almost gentle. But this peaceful appearance hides a truth that scientists have known for decades. The sun is not calm. It is not quiet. It is a colossal, violent, and unstable sphere of plasma, constantly erupting, twisting, and unleashing storms powerful enough to affect the entire solar system. And now, as we move deeper into the decade, the sun is entering one of its most active phases, a period known as the solar maximum. The question is no longer whether solar storms will intensify, but what will happen when they do. And more importantly, what happens if one of those storms strikes Earth with the force of the most powerful solar event in recorded history? To understand the danger, we have to begin with the nature of the sun itself. The sun is not a solid object like a planet. It is a massive ball of superheated plasma, where hydrogen atoms fuse into helium at its core, releasing unimaginable amounts of energy. This energy travels outward, eventually reaching the surface, where it erupts into space as heat, light, and charged particles. But the sun does not release this energy evenly. Its surface is constantly shifting, twisting, and tearing under the influence of its own magnetic fields. These magnetic fields are not stable lines. They move, stretch, tangle, and snap. And when they snap, they release enormous bursts of energy known as solar flares and coronal mass ejections. A solar flare is a sudden flash of radiation, often lasting only minutes but powerful enough to affect radio communications on Earth. A coronal mass ejection, or CME, is even more dramatic. It is a massive cloud of charged particles and magnetic energy that explodes outward from the sun's surface, sometimes traveling millions of kilometers per hour. When a CME is directed toward Earth, it becomes what scientists call a geomagnetic storm. Most of the time, Earth is protected by its magnetic field, an invisible shield generated by the movement of molten metal in the planet's core. This magnetic field deflects most of the sun's charged particles, guiding them harmlessly toward the poles. When these particles collide with the atmosphere, they create the glowing curtains of light known as auroras. For most people, this is the only visible sign of solar activity, a beautiful, silent dance of color in the night sky. But sometimes, the sun releases storms that are far more powerful than usual. And when that happens, the auroras are only the beginning. The sun operates on an approximately 11-year cycle. During the quiet phase, known as solar minimum, the sun's surface is relatively calm. There are fewer sunspots, fewer flares, and fewer eruptions. But as the cycle progresses, solar activity begins to increase. Sunspots dark, cooler regions on the sun's surface multiply. These sunspots are signs of intense magnetic activity, and as their numbers grow, so does the likelihood of solar flares and coronal mass ejections. Eventually, the sun reaches solar maximum, the peak of this activity cycle. During this time, the sun can unleash powerful storms with little warning. Scientists have been monitoring the current solar cycle closely, and all signs indicate that the sun is approaching or entering this maximum phase around 2025 to 2026. For skywatchers, this is an exciting time. Auroras become more frequent and more intense. In some cases, they can be seen much farther from the poles than usual. Cities that rarely experience auroras may suddenly find their skies glowing with green, red, or purple light. But for engineers, power companies, and satellite operators, solar maximum is a time of concern. The reason is simple. Modern civilization depends on technology that is extremely vulnerable to space weather. Satellites orbiting Earth are constantly exposed to the sun's charged particles. Power grids rely on long transmission lines that can act like antennas for geomagnetic currents. GPS systems, aviation communications, and internet infrastructure all depend on stable electromagnetic conditions, and solar storms can disrupt all of them. To understand how serious this threat can be, we have to go back to the year 1859, to the most powerful solar storm ever recorded, the Carrington Event. In late August of that year, the sun unleashed a massive coronal mass ejection toward Earth. At the time, there were no satellites, no power grids, and no internet. The world was far less dependent on electricity. But there was one technology that connected continents: the telegraph. When the solar storm reached Earth, it triggered intense geomagnetic currents across the planet. Telegraph systems began to behave strangely. Operators reported sparks flying from their equipment. Some telegraph lines caught fire. Others continued to transmit messages even after their power supplies were disconnected. Powered entirely by the electrical currents induced by the storm, auroras were seen across the globe, even near the equator. In some places, the night sky became so bright that people thought it was dawn. Newspapers reported that miners in the Rocky Mountains woke up in the middle of the night and began making breakfast. Believing morning had arrived, it was a stunning display of nature's power. But it also offered a glimpse of what could happen if such a storm struck a more technologically dependent world. Today, the stakes are far higher. Our modern infrastructure is deeply interconnected and heavily reliant on electricity and satellites. A Carrington-level event today would not just create sparks in telegraph lines. It could damage or destroy transformers and power grids, disable satellites, disrupt GPS, and knock out large portions of the internet. Large power transformers are especially vulnerable. These devices are critical to the operation of electrical grids. They step voltage up or down, allowing electricity to travel long distances efficiently. But they are also expensive, heavy, and difficult to replace. Some weigh hundreds of tons and require months or even years to manufacture. During a severe geomagnetic storm, electrical currents can flow through the ground and into power lines. These currents can overload transformers, causing them to overheat, fail, or even explode. If enough transformers are damaged, entire regions could lose power for extended periods. In a world where nearly everything depends on electricity, from water systems to hospitals to communication networks, the consequences could be severe, but the danger does not stop at the power grid. Satellites are also at risk. Satellites orbit Earth in a delicate balance between gravity and speed. They rely on precise positioning and stable conditions to function properly. But during a solar storm, the upper atmosphere heats up and expands. This increased atmospheric drag can cause satellites to lose altitude. If the storm is strong enough, satellites can re-enter the atmosphere and burn up. This is not just a theoretical concern. In 2022, a solar storm caused dozens of newly launched satellites to fall out of orbit shortly after deployment. The storm increased atmospheric drag, and the satellites could not maintain their positions. Now, imagine that scenario on a much larger scale. Thousands of satellites, including those that provide internet services, GPS navigation, weather monitoring, and communications, could be affected. Without satellites, modern life would change dramatically. GPS would become unreliable. Aviation and shipping would face navigation challenges. Weather forecasting would become less accurate. Satellite internet services could be disrupted or lost entirely. And this leads to one of the most pressing questions of the solar maximum. Could a solar storm destroy the internet? The answer is complex. The internet is not a single structure. It is a vast network of cables, servers, satellites, and infrastructure spread across the globe. Some parts of it are more vulnerable than others. One major concern is undersea cables. These cables carry the majority of international internet traffic. They stretch across oceans, connecting continents through fiber optic lines. While the fiber itself is not affected by electromagnetic storms, the repeater's devices placed along the cable to boost the signal are powered by electricity. If geomagnetic currents interfere with these systems, communication across continents could be disrupted. Another concern is data centers. These facilities house the servers that store and process information. They rely heavily on stable power supplies. If power grids fail, data centers must switch to backup generators. But if outages last for weeks or months, maintaining operations becomes difficult. The combination of satellite disruptions, power grid failures, and cable interference could create a cascading effect. Systems that depend on each other could begin to fail in sequence. Communication networks could slow down or collapse in certain regions. Financial systems could be disrupted. Supply chains could stall. The modern world, built on constant connectivity, would face a sudden and unfamiliar reality. And yet, scientists emphasize that not all solar storms are catastrophic. Many pass with little more than increased auroras and minor disruptions. Space agencies around the world monitor the sun constantly, watching for signs of major eruptions. Satellites like the Solar Dynamics Observatory and the Solar and Heliospheric Observatory provide early warnings of solar activity. When a coronal mass ejection is detected heading toward Earth, scientists can often predict its arrival within 1 to 3 days. This warning time allows power companies to take protective measures, such as reducing grid loads or temporarily shutting down vulnerable systems. But even with warnings, a truly extreme event could still cause significant damage. The question is not whether solar storms will happen. They always do. The question is whether one will occur that is powerful enough to test the limits of our technological defenses. And as the sun approaches its maximum activity phase, that question becomes more urgent as scientists look ahead to the peak of the current solar cycle. They are not simply watching the sun out of curiosity. They are watching it because the stakes are higher than at any point in human history. Never before has civilization depended so heavily on fragile electronic systems. Never before have so many satellites orbited the Earth. Never before has the global economy relied so completely on constant digital communication. The modern world is built on invisible network signals, cables, servers, and satellites, and all of them exist under the influence of the sun. During solar maximum, the sun's magnetic field becomes more chaotic. Sunspots multiply across its surface, each one a region of intense magnetic stress. These sunspots are not harmless blemishes. They are warning signs. Around them, magnetic loops twist and stretch, storing enormous amounts of energy. When those magnetic fields snap or reconnect, they release that energy in violent bursts. These bursts can take the form of solar flares, which travel at the speed of light, or coronal mass ejections, which are slower but far more dangerous. A solar flare can disrupt radio signals almost instantly. A coronal mass ejection, however, carries billions of tons of charged particles and magnetic energy across space. When that cloud reaches Earth, it interacts with the planet's magnetic field, sometimes with dramatic consequences. One of the most concerning aspects of solar storms is that their impact depends not only on their strength, but also on their magnetic orientation. If the magnetic field of a coronal mass ejection is aligned in a certain way opposite to Earth's magnetic field, it can effectively punch a hole in our planet's protective shield. This allows charged particles to pour into the magnetosphere, intensifying the storm. It is a bit like two magnets being forced together. If their poles repel, they resist each other. But if their poles attract, they snap together suddenly. When the sun's magnetic field aligns in a way that connects with Earth's, energy flows into the system rapidly. This is when geomagnetic storms become most dangerous. In 1989, a solar storm provided a modern example of what can happen. That year, a coronal mass ejection struck Earth and triggered a geomagnetic storm strong enough to collapse the power grid in Quebec, Canada. In less than 2 minutes, the entire province went dark. 6 million people lost electricity. The outage lasted for 9 hours, and the effects rippled through transportation, business, and daily life. That storm was not even close to the strength of the Carrington Event. It was a fraction of its power, and yet it was strong enough to cause widespread disruption. Since 1989, our dependence on electricity and digital systems has increased dramatically. Power grids have grown larger and more interconnected. The internet has become the backbone of communication, commerce, and information. Satellites now support everything from banking transactions to navigation apps on smartphones. A storm similar to the one that hit Quebec today could have far greater consequences. And a Carrington-level event could be far more serious. Scientists have attempted to estimate the impact of such a storm on modern society. Some studies suggest that a severe geomagnetic storm could cause widespread power outages affecting tens of millions of people. In the worst-case scenarios, the economic damage could reach trillions of dollars. But beyond the economic impact, there is a more immediate concern: time. Large power transformers, the backbone of electrical grids, are not easy to replace. They are custom-built, often designed for specific locations. Manufacturing a single transformer can take months. Transporting it can be a logistical challenge, requiring specialized vehicles and infrastructure. If a solar storm damaged dozens or hundreds of these transformers at once, replacement could take years. During that time, affected regions could experience prolonged power shortages. Without electricity, many of the systems we rely on would stop functioning. Water treatment plants would struggle to operate. Fuel pipelines could shut down. Refrigeration systems would fail, affecting food supplies. Hospitals would rely heavily on backup generators, which themselves depend on fuel deliveries. Communication systems would also be affected. Cell towers require electricity. Internet routers and data centers require stable power. Even if some systems remained operational, the overall network could become slow, fragmented, or unreliable. The internet, often thought of as a decentralized and resilient system, still depends on physical infrastructure. Data must travel through cables, routers, and servers. If enough of these components lose power, the network begins to break apart. International connections are especially vulnerable. Undersea cables carry the majority of global internet traffic. These cables rely on repeaters placed along their length to amplify signals. If geomagnetic currents disrupt the power supply to these repeaters, entire transoceanic connections could fail. This could isolate continents from one another in terms of digital communication. Financial markets could become disconnected. Cloud-based services could become inaccessible. Businesses that rely on real-time data could be forced to shut down operations. The effects would not be uniform across the globe. Some regions would be more affected than others. Areas at higher latitudes, closer to the poles, are more exposed to geomagnetic storms. These regions often experience the strongest auroras and the strongest electrical currents during solar events. Countries like Canada, the United States, the United Kingdom, and the Nordic nations could be particularly vulnerable. But because the global economy is interconnected, disruptions in one region could have ripple effects worldwide. Supply chains could slow or collapse. Financial systems could become unstable. Communication between countries could be delayed or interrupted. Yet despite these risks, there is also reason for cautious optimism. Unlike in 1859, we now understand the sun much better. We have satellites dedicated to monitoring solar activity. We can detect solar flares almost instantly. We can track coronal mass ejections as they travel through space. We can estimate their speed, direction, potential impact. This gives us time to prepare. Power companies can temporarily shut down vulnerable parts of the grid. Satellites can be placed into safe modes. Airlines can reroute flights away from polar regions. Where communication disruptions are more likely, these measures do not eliminate the risk, but they can reduce the damage. Engineers are also working to make infrastructure more resilient. Some power grids are being redesigned to handle geomagnetic currents more safely. Satellite components are being hardened against radiation. Early warning systems are becoming more sophisticated. Still, the challenge is enormous. The sun is a force far beyond human control. A single large eruption can release more energy than billions of nuclear bombs combined. And space, vast and empty as it seems, offers little protection when that energy is directed toward Earth. There is also the problem of unpredictability. While we can monitor solar activity, we cannot always predict exactly when a major eruption will occur. The sun's magnetic fields are complex and dynamic. They behave in ways that are not fully understood. Sometimes large sunspot groups appear suddenly. Sometimes they release massive flares with little warning. And sometimes storms that appear mild can become more intense as they travel through space. In July 2012, Earth narrowly avoided what could have been a modern Carrington-level event. A massive coronal mass ejection erupted from the sun and traveled through Earth's orbit. But by sheer coincidence, our planet was not in its path at the time. If the eruption had occurred just a few days earlier, it would have struck Earth directly. Scientists later estimated that the storm was comparable in strength to the Carrington Event, had it hit Earth. The consequences could have been severe. This near miss serves as a reminder that extreme solar storms are not just historical curiosities. They can happen again. And when they do, they may test the resilience of our technological civilization. As we move deeper into the solar maximum of the mid-2020s, the sun's activity is expected to continue increasing. More sunspots will appear. More flares will erupt. More coronal mass ejections will be launched into space. Most of them will miss Earth. Some will produce only minor effects. But the possibility of a major event remains. The question is not whether the sun is capable of producing such a storm. It has done so before. The question is whether our modern world is ready for it. And that question leads to a deeper reflection on the nature of our technological age. We have built a civilization that depends on invisible systems, signals that travel at the speed of light, data that flows across oceans in thin strands of glass, satellites that circle the planet thousands of times each year. These systems have given us incredible power, instant communication, global navigation, access to knowledge from anywhere on Earth. But they have also created new vulnerabilities. A storm on the surface of a distant star 150 million kilometers away, reach across space and disrupt the networks that hold our world together. It is a reminder that, for all our technological progress, we are still connected to the forces of nature. The sun that warms our planet is the same sun that can threaten our infrastructure. The same star that makes life possible can also challenge the systems we have built. And as the solar maximum approaches, that connection becomes more visible, more dramatic, and more important than ever, as scientists and engineers consider the possibility of an extreme solar storm. The question is no longer limited to what the sun might do. The more pressing question is how prepared humanity is to handle it. Around the world, governments, space agencies, and private companies are quietly working to understand and reduce the risks of space weather. But the scale of the challenge is immense, and preparation is uneven. Space weather forecasting has become a serious scientific discipline. Agencies like NASA, the European Space Agency, and National Weather Services operate satellites dedicated to monitoring the sun. These spacecraft watch for sunspots, track solar flares, and measure the flow of charged particles streaming through space. When a major eruption occurs, scientists can often detect it within minutes, once a coronal mass ejection is observed, leaving the sun. Researchers use models to estimate its speed and direction. If it appears to be heading toward Earth, alerts are sent out. These warnings can give anywhere from several hours to a few days of preparation time. Depending on the speed of the storm, this early warning system is one of the most important defenses we have. Power companies can take steps to reduce stress on the grid. Satellites can be switched into protective modes. Astronauts aboard space stations can move into shielded areas. Airlines can reroute flights to avoid communication blackouts near the poles. But these measures are not foolproof. A truly powerful storm could still overwhelm defenses, especially if it arrives faster than expected or has an unusually strong magnetic orientation. The difficulty lies in the complexity of modern infrastructure. Power grids, communication networks, transportation systems, and financial markets are all interconnected. A disruption in one area can quickly spread to others. Imagine a severe solar storm striking Earth. Within hours, geomagnetic currents begin flowing through the ground and into power lines. In high-latitude regions, transformers start to overheat. Some shut down automatically to protect themselves. Others fail completely. Cities lose power. Traffic lights stop working. Subways grind to a halt. Elevators freeze between floors. Hospitals switch to backup generators. At first, the outages seem like routine blackouts. But as hours turn into days, the scale of the problem becomes clear. Repair crews discover that some transformers are damaged beyond repair. Replacements are not available locally. They must be ordered from manufacturers, and the waiting list is long. Other countries are facing the same problem. Everyone is competing for the same limited supply of equipment. Meanwhile, communication networks begin to struggle. Cell towers lose power. Internet service providers experience outages as data centers shut down or switch to backup systems. In some regions, the internet slows to a crawl. In others, it disappears entirely. Satellites, exposed to increased radiation and atmospheric drag, start to malfunction. Some lose their orientation. Others drop out of orbit. GPS signals become unreliable. Navigation systems in cars, ships, and aircraft begin to fail. Airlines cancel flights. Shipping companies delay departures. Financial markets struggle to operate as communication between trading centers becomes unstable. Digital transactions slow down or stop altogether. Within days, the effects begin to spread beyond the technological world into daily life. Without reliable power, water treatment plants cannot operate at full capacity. Some areas experience water shortages. Gas stations cannot pump fuel without electricity. Supermarkets struggle to keep food refrigerated. Supply chains, already stretched thin in many parts of the world, begin to break down. Deliveries are delayed. Shelves grow emptier. Panic buying may begin in some regions, adding to the strain. In the most severe scenarios, these disruptions could last for weeks or even months, depending on the damage to critical infrastructure. But it is important to note that such a scenario represents the worst case. Not every solar storm would cause this level of disruption. Many storms pass with only minor effects, and even in a severe event, the impact would vary by region. Some parts of the world, especially those closer to the equator, would experience less intense geomagnetic currents. Their power grids might remain largely intact. Communication systems might continue to function, at least partially. This uneven impact could create a patchwork of connectivity. Some regions would remain online, while others would struggle. International communication could become slower and less reliable, but not necessarily disappear entirely. The internet, in particular, is more resilient than many people assume. It was originally designed to survive disruptions. Data can often be rerouted through alternative paths. If one connection fails, another may take its place. However, the scale of a Carrington-level event could test that resilience. If multiple systems fail, simultaneously, power grids, satellites, undersea cables, the network's ability to adapt could be overwhelmed. Researchers have studied this possibility, examining how geomagnetic storms could affect undersea cables. These cables span thousands of kilometers, with repeaters placed along their length to boost signals. The repeaters rely on electrical power transmitted through the cable itself. During a strong geomagnetic storm, currents induced in the Earth's surface could interfere with this power system. If enough repeaters fail, entire cable segments could go offline. This could sever connections between continents, forcing data to take longer, less efficient routes. In some cases, there may be no alternative route at all. Regions that rely heavily on a small number of undersea cables could become digitally isolated. This raises the possibility of a partial internet blackout, where some parts of the world remain connected while others experience severe disruptions. But even in such a scenario, the internet would not necessarily disappear entirely. Local networks could continue to function. Data stored on local servers would still be accessible. Communication within unaffected regions could continue. The real danger lies in the loss of global connectivity. The modern internet is built on the assumption that information can travel instantly across the planet. If that assumption breaks down, many systems that depend on real-time data could fail. Financial markets, for example, rely on constant communication between trading centers. A delay of even a few seconds can have major consequences. If connections between major financial hubs were disrupted, markets could become unstable or shut down entirely. Cloud-based services would also be affected. Many businesses rely on remote servers to store data and run applications. If those servers become inaccessible, operations could grind to a halt. In such a scenario, the world would experience something unfamiliar, a sudden reduction in digital speed. Tasks that once took seconds could take minutes or hours. Communication that once felt instantaneous could become slow and uncertain. For a generation accustomed to constant connectivity, this would be a profound change. Yet even in the face of these possibilities, scientists emphasize that the risk, while real, is not inevitable doom. Infrastructure is being improved. Awareness is growing, and technology continues to evolve. Some power grids are being redesigned to better withstand geomagnetic storms. Protective devices can block harmful currents. Monitoring systems can detect problems early. Satellite operators are developing more radiation-resistant components. Some companies are exploring ways to build satellite constellations that can recover quickly from losses. Researchers are also studying how to make undersea cables more resilient, reducing the risk of widespread communication failures. Preparation is ongoing. Though it is a race against time and uncertainty, the sun will continue its cycles, as it always has. Solar maximum will come and go. Activity will rise and fall. The question is whether humanity's preparations will keep pace with the sun's power. For now, solar maximum of the mid-2020s represents both a warning and an opportunity. It is a reminder of our connection to the forces of nature. and it is a chance to strengthen the systems that support modern life. Because the sun is not an enemy. It is the source of life on Earth, but it is also a powerful, unpredictable star. And as we build a civilization increasingly dependent on delicate technologies, we must learn to live not only under its light, but also under its storms. If a truly severe solar storm were to strike Earth, the most important question would not be how dramatic the auroras looked, or how many satellites were damaged. The most important question would be how long it would take for life to return to normal. And that answer would depend on one thing above all else: time. In the first hours after a major geomagnetic storm, the effects would feel confusing rather than catastrophic. Power outages would occur in some regions, while others would remain unaffected. Communication networks might slow down or behave unpredictably. Some satellites would malfunction, while others would continue operating normally. People would turn to their phones, computers, and televisions to understand what was happening. But in some places, those very systems would be unreliable. News would travel unevenly, spreading quickly in connected regions and slowly in disconnected ones. Within the first day, the situation would become clearer. Power companies would begin assessing damage to transformers and transmission lines. Satellite operators would attempt to regain control of affected spacecraft. Governments would issue statements, urging calm and explaining the situation. In many areas, electricity would return quickly. Modern grids are designed with redundancy. If one part fails, another can often take its place. But in regions where key transformers were damaged, the outages could last longer. After several days, the focus would shift from immediate response to recovery. Crews would begin repairing equipment. Temporary solutions would be implemented. Mobile generators might be deployed to critical facilities. But if the storm had caused widespread transformer failures, the recovery process could stretch into weeks or months. Manufacturing replacements takes time. Transporting them requires planning and coordination. Installing them involves complex engineering work. During this period, daily life would change in noticeable ways. In areas without stable electricity, businesses would operate on reduced hours or shut down entirely. Schools might close. Public transportation systems could be limited or suspended. Water and food supplies would become major concerns. Without electricity, water treatment plants cannot operate at full capacity. Pumping stations may fail. In some areas, water pressure could drop or disappear altogether. Food distribution would also be affected. Refrigeration systems would struggle. Supply chains would slow down. Supermarkets might see shortages, especially if transportation networks were disrupted. In such conditions, communities would rely heavily on local resources. Neighborhoods might organize shared meals or distribute supplies. Local authorities would coordinate relief efforts. The sense of community could become stronger as people worked together. To overcome the challenges, communication would also change. In areas where the internet was disrupted, people might rely more on radio broadcasts or local information centers. Word of mouth could once again become an important way of sharing news. As weeks passed, the global economy would begin to feel the strain. Financial markets rely on constant communication and stable power. If those systems were disrupted, trading could slow down or stop. Businesses that depend on digital infrastructure would struggle. Online services might become unreliable. Cloud-based platforms could be inaccessible in some regions. Remote work would become difficult or impossible where connectivity was lost. International trade would also be affected. Shipping and aviation rely on satellite navigation. Without reliable GPS, routes would need to be recalculated using older, less efficient methods. This could slow down the movement of goods across the globe. Despite these challenges, recovery would be underway. Replacement transformers would begin arriving. Power grids would gradually come back online. Communication networks would be repaired. In many places, life would return to something close to normal within a few weeks. In others, especially those hit hardest, recovery could take much longer. The long-term impact would depend on the scale of the storm. A moderate but widespread event might cause temporary disruptions and economic losses, but systems would recover. A truly extreme event, on the level of the Carrington Event, could leave lasting scars on infrastructure and economies. Yet history shows that humanity is remarkably adaptable. After natural disasters, wars, and global crises, societies have rebuilt. Infrastructure has been repaired. Technologies have improved. A major solar storm would be a challenge, but not necessarily the end of modern civilization. In fact, it could lead to important changes. Governments might invest more in resilient infrastructure. Power grids could be redesigned to handle geomagnetic currents more safely. Communication networks might be built with greater redundancy. Satellite systems could become more robust. New materials and technologies could make spacecraft more resistant to radiation. Early warning systems could be expanded, giving more time to prepare for future storms. The event could serve as a wake-up call, reminding humanity of its vulnerability to space weather. Just as past disasters have led to improvements in safety and preparedness, a solar storm could drive innovation and resilience. It is also worth remembering that extreme solar storms are rare. The Carrington Event was an outlier, not a common occurrence. While the sun goes through cycles of activity, truly massive eruptions are infrequent. Scientists estimate that a Carrington-level storm may occur once every century or two. That means the probability of such an event in any given year is relatively low. But the consequences are significant enough that preparation is essential. There have also been several near misses in recent decades. The 2012 solar storm that narrowly missed Earth is one example. It was a reminder that extreme events are still possible. Even in the modern era, as the sun moves through its cycles, the risk rises and falls. Solar maximum increases the likelihood of strong storms, but it does not guarantee a catastrophic event. For most people, the solar maximum will be remembered not for blackouts or disruptions, but for something far more beautiful, the EURO. As solar activity increases, the northern and southern lights become more intense and more widespread. People in regions that rarely see them may suddenly find their night skies glowing with color. Green curtains of light may ripple across the horizon. Red and purple streaks may dance overhead. Entire cities could find themselves under shimmering skies, lit by the energy of the sun. These displays are the visible side of space weather. They are the reminder that Earth is part of a much larger system. Connected to the sun by invisible streams of energy, the same solar storms that threaten satellites and power grids also create some of the most beautiful sights in nature. It is a reminder that the forces of the universe are neither good nor bad. They simply are. The sun does not intend to harm or help. It burns, it erupts, it cycles through its phases, just as it has for billions of years. Human civilization, on the other hand, is young and delicate. Our technologies are powerful, but they are also vulnerable. A storm from the sun can remind us of that vulnerability in a very real way. And perhaps that reminder is valuable. It encourages us to build stronger systems, to prepare for unexpected challenges, to recognize that we are still part of a natural universe, not separate from it. As the solar maximum of the mid-2020s unfolds, scientists will continue watching the sun. Satellites will track its storms. Engineers will strengthen infrastructure. Governments will plan for possible disruptions. Most likely, life will continue as usual. There will be more auroras, more solar flares, and perhaps a few minor disruptions. But the internet will keep running. Power grids will keep humming. Satellites will keep orbiting, and yet somewhere on the surface of the sun, magnetic fields will continue to twist and stretch. Energy will continue to build, and at some point, whether this cycle or the next, the sun will unleash another major storm when that day comes. The world will once again be reminded of the star at the center of our solar system. The same star that gives us light, warmth, and life. And the same star that holds the power to test the very systems we depend on. The question is not whether the sun will storm again. The question is whether, when it does, humanity will be ready. As discussions about solar storms become more common, one question appears again and again. How likely is a truly catastrophic event in our lifetime? It is a question that scientists approach with caution because the sun does not follow human schedules. It operates on cycles, patterns, and magnetic forces that are still not fully understood. Historical data gives us some clues. The Carrington Event of 1859 remains the strongest solar storm ever recorded. Since then, there have been several powerful storms, but none quite as intense. The 1921 New York Railroad storm caused widespread telegraph and railway disruptions. The 1989 Quebec blackout demonstrated how even a moderate geomagnetic storm could collapse a modern power grid. And the 2003 Halloween storms caused satellite failures, communication disruptions, and power issues across multiple countries. Then there was the near miss of 2012, when a massive coronal mass ejection passed through Earth's orbit just days after our planet had moved out of the way. Scientists later concluded that the storm was comparable in strength to the Carrington Event. Had it struck Earth directly, it might have caused widespread technological damage. Events like these suggest that extreme solar storms are not theoretical possibilities. They are part of the sun's natural behavior, but they are rare. Studies of ice cores and tree rings, which can record traces of solar activity, suggest that storms on the scale of the Carrington Event may occur once every 100 to 200 years. That means humanity lives under a quiet long-term risk. Most generations will never experience such an event, but eventually, one will. The solar maximum of the mid-20s is not expected to produce a Carrington-level storm. Most forecasts suggest that this cycle will be moderate to strong, but not extreme. Still, solar cycles are unpredictable. The sun does not always follow expectations. Some cycles produce unexpected bursts of activity, while others remain relatively calm. Because of this uncertainty, space agencies treat every solar maximum as a period of heightened awareness. Satellites are monitored more closely. Power companies review their emergency plans. Scientists study sunspot activity with renewed attention. But beyond the short-term cycle, researchers are also thinking about the long-term future. As humanity becomes more technologically advanced, our exposure to space weather increases. One major development is the rapid growth of satellite constellations. In recent years, thousands of satellites have been launched into low Earth orbit, providing internet services, communication links, and observation capabilities. Companies are planning to launch tens of thousands more in the coming decades. These constellations are designed to be resilient. Individual satellites are relatively small and inexpensive. If some fail, others can take their place. But they are also more exposed to solar activity, especially in low Earth orbit, where atmospheric drag increases during solar storms. A severe solar maximum could lead to increased satellite losses, forcing companies to launch replacements more frequently. This could raise costs and complicate operations, but it is unlikely to destroy entire constellations unless the storm is extremely powerful. Another area of concern is deep space exploration. As humans plan missions to the moon and Mars, solar storms become a serious threat. Outside Earth's magnetic field, astronauts are far more exposed to radiation. A strong solar flare or coronal mass ejection could deliver dangerous doses of radiation in a short time. Space agencies are working on shielding solutions, storm shelters, and early warning systems to protect crews during solar events in this way. The challenge of space weather is not limited to Earth. It extends into the future of human exploration back on Earth. Engineers are also rethinking the design of critical infrastructure. Some power grids are being equipped with devices that can block geomagnetically induced currents. Others are being redesigned to reduce the risk of transformer damage. Data centers. The backbone of the internet are being built with greater redundancy. Many now have multiple power sources, backup generators, and distributed server networks. This means that even if one facility goes offline, others can take over its functions. Undersea cable systems are also evolving. Newer cables are designed with improved power systems and monitoring tools, allowing operators to detect, respond to problems more quickly. All of these changes are part of a broader shift toward resilience. Instead of assuming that systems will always operate under ideal conditions, engineers are preparing for disruptions. This shift reflects a deeper understanding of the world we live in. Earth is not an isolated island in space. It is part of a dynamic solar environment. The sun's activity affects our planet in ways both beautiful and dangerous. Auroras, after all, are not just pretty lights. They are the visible signs of energy flowing from the sun into Earth's atmosphere. They are reminders that our planet is constantly interacting with its star. During solar maximum, these displays become more frequent and more intense. People far from the polar regions may see auroras for the first time. Entire cities may watch the sky glow with colors they have never seen before. For many, this will be the most visible sign of the sun's increased activity. They will look up at the sky, take photos, and share them online. Unaware of the invisible forces moving through space, and in a way, that is the quiet paradox of solar storms. The same event that creates breathtaking beauty in the sky can also threaten the technologies that support modern life. It is a reminder of balance. The sun is not just a source of danger. It is the source of everything we depend on. Without it, Earth would be a frozen, lifeless world. Solar storms are part of that same system. They are the natural byproducts of the sun's magnetic activity. They are signs of a star that is alive, dynamic, and powerful. As we move further into the 21st century, humanity's relationship with the sun will become more complex. We will rely more on satellites, more on digital systems, more on technologies that are sensitive to space weather at the same time. Our ability to monitor and predict solar activity will improve. New satellites will watch the sun from different angles. Advanced models will help scientists understand its behavior more accurately. One day, we may even have the ability to forecast solar storms with the same confidence that we forecast hurricanes on Earth. We may know days or weeks in advance. When a major eruption is likely until then, we live in a state of cautious awareness. The sun is both familiar and unpredictable. It rises each day, as it always has. But beneath that familiar glow lies a constant. Its powerful activity, the solar maximum of 2026, is just one chapter in that ongoing story. It will bring brighter auroras, more frequent flares, and perhaps a few disruptions. But it will also bring new insights, new technologies, and new preparations. And somewhere, deep within the sun's turbulent surface, magnetic fields will continue to twist and coil. Energy will continue to build. And eventually, whether in this cycle or a future one, the sun will release another great storm. When that happens, humanity will face a test not just of technology, but of resilience, of preparation, of cooperation, because no single country, company, or agency can face a solar storm alone. Space weather is a global phenomenon. Its effects cross borders, oceans, and continents. And perhaps that is the final lesson of the solar maximum. It reminds us that we share a single planet, orbiting a single star. The forces that affect one part of the world can affect all of it. The sun does not recognize nations, economies, or technologies. It simply burns, as it always has, and under its light. Humanity must learn not just to survive, but to adapt, prepare, and endure, ready for the next great storm that may come from the sky.